this video, we will review operators derived from the gradient operator. In particular, we will review the gradient operator itself, del, as well as how the del operator works, and in particular the so-called hungriness of the del operator, which is then used to derive other vector operations such as divergence, curl, and some higher order operators that we will be using later. So to review, the gradient of a three-dimensional function in Cartesian coordinates is given by this expression, where f is a scalar function of all three spatial variables. So you can see the input here is a scalar, but the output of the vector operation, or of this gradient operation, is a vector. We can factor this expression and pull the derivatives as well as the unit vectors out into parentheses here, and that operation in parentheses can be called the del operation on f. So f would have to be multiplied through for each component in order to lead to the expression above. This leads to an interesting property of del, which is the so-called hungriness of the operator. So previously we considered del f, and if we multiply f through each term in parentheses, we arrive at the gradient operator. But if we were to consider the opposite order, f del, we would get something different. F still needs to be distributed amongst the three terms in parentheses, but these derivatives are still hungry, so to speak, to act on something here. So del f is not the same thing as f del, and we need to add something after for the derivatives to act on. And this property is useful for deriving some vector operations involving the del operator. The first of these is divergence. So divergence is denoted del dot f, where f is a vector. So if we substitute in the operation for del that we just showed for the x, y, and z components, we can now dot this with a vector f, which has, say, an x component f sub x, a y component f sub y, and a z component f sub z. Now this is just like a regular scalar product between two vectors. So we take each component of the vectors, multiply them together, and then add everything together. So if we do the x component first, we need to take the partial derivative of f sub x with respect to x, and then add to that the multiplication of the next term, which is the partial derivative of f sub y with respect to y, and the same thing for f sub z. And this is the divergence operation. So we note that the input to divergence is a vector, but the output of the operation is a scalar. And we could guess this from the fact that we know that when we dot two vectors together, the output is a scalar. So this is an important thing to remember, because when we use divergence in the context of electromagnetics, the output will be a scalar quantity or a scalar field. We can also use the del operator to derive curl, which we will consider later for magnetic fields. So the curl of a vector f is denoted as del cross f. So in this case, we expect to get a vector at the conclusion of this operation, because cross product takes a vector, multiplies it with another vector, and yields the vector or cross product. So we should get a vector at the conclusion of this. Again, we can substitute in the expression for the del operator, shown here. And now we will take the cross product with f, which we again expand in terms of its x, y, and z components. Now usually when we do cross products, we write this in determinant form. So we can write a matrix determinant here with the first row consisting of the unit vectors. The second row is the first vector that we want to take the dot product with. So this is the partial derivatives. And the last row is f, or the components of f sub x, f sub y, and f sub z. So now we can follow through and compute each subdeterminant in turn. So if we want to do the x component, we need to consider the bottom right determinant, which is going to be the partial derivative of fz with respect to y minus the partial derivative of fy with respect to z, and this will be the x component. Then we consider this the determinant comprised of the first and third columns, and we need to remember that there's a minus sign for that one. So now we take the partial derivative of fz with respect to s and subtract the partial derivative of fx with respect to z, and this will be the y component. And then for the z component, we're back to a positive term, and we do the subdeterminant on the bottom left, which is the partial derivative of fy with respect to x minus the partial derivative of fx with respect to y, and attach the z unit vector. And this is the definition of curl that you'll find on a reference sheet, for example, and it can be derived very easily using this determinant. Another operation that we will use in the course is Laplacian. Laplacian is an example of a second order operation because there are second order derivatives in this operator. So Laplacian comes about by taking the divergence of the gradient of some scalar field, maybe we would call that field t. So just as before, we can expand these, but first I'll note that this is usually written more commonly as del squared t, and this del squared is called Laplacian. So let's expand the operations on the left. Again, we can expand our del operator as a vector, as shown here. And on the right, we have the gradient of t, which we've written at the very beginning of this video. So we can write this as follows. So now it's just a matter of following through with our scalar product, much like we did for the divergence operation, but we will now get three terms and a scalar, but we will have the second derivative of t with respect to each individual component. So again, a reminder that the output of this particular operation, it acted on a scalar, and the output is also a scalar because of the dot product. So we can derive many other vector operations from the del operator. These are the most useful ones for the purposes of electromagnetics. But on your own, you might consider deriving some other operators, and a possible list to try is shown here. So good luck, and thanks for watching this video.